The views and opinions expressed on Coffee and Compatibility are those of the podcast host and do not necessarily reflect the official policy or position of ASHI.
Hello, Coffee and Compatibility audience. Today we are honored. I'm already getting red just before I'm saying it. We are very honored to be joined by one of the world's leading pioneers in regenerative medicine, Dr. Anthony Atala. Dr. Atala is the director of the Wake Forest Institute for Regenerative Medicine, where he is doing groundbreaking work in tissue engineering, stem cell research, and 3D bioprinting. He's totally helped to redefine what's possible in modern medicine. His team has been responsible for numerous first-in-human regenerative medicine technologies, and his research continues to shape the future of transplantation and patient care around the world. Dr. Atala will be a featured speaker at the 2026 ASHI Annual Meeting in Montreal, where he'll discuss the exciting future of regenerative medicine and its impacts on transplantation. Dr. Atala, thank you so much for being with us today. Oh, I can't believe I'm asking you this, but may we call you Tony?
Please do. And it's really great to be with all of you. What a treat. And so very much looking forward to being at the meeting.
Thank you so much. I feel like the listeners of today's episode are spoiled for so many reasons. Reason number one, because you're the guest and some would consider you like a father of regenerative medicine. But also because the people who listen to this episode might get a few spoilers for what you might talk about at the annual meeting. And it is really, really exciting. So if you would start by telling us a little bit more about your laboratory at Wake Forest, about the Institute for Regenerative Medicine, and what your study focus has been.
Yeah, thank you, Kelly. Appreciate it. So basically, as you know, Regen Med, of course, I'm sure it's a common terminology for the society, but working on building tissues and organs and using cells for therapies, and we are working on about 40 different tissues and organs and trying to get as many of those to patients as we can, and really just continuing to work so we can reach as many patients as possible.
So, Dr. Atala, where are we today in terms of this technology? What tissues or organs are able to be engineered and then implanted into patients in a way that they're actually functional?
Yeah, thank you, Jeremy. So basically, we have about 18 technologies that we've transferred to patients at this point. I always like to say there's a complexity to tissues and organs, with flat structures like skin being the least complex because you're, flat architecturally, but they're all complex. Even skin is extremely complex, right? Over 6 different cell types, 3 different layers. But architecturally is the least complex. And then you have tubular structures like blood vessels, which are the second level of complexity because you're allowing air fluid to go through at a steady state. And then you have hollow non-tubular organs being the third level of complexity, like the bladders or the uterus or the stomach. And finally, the most complex, of course, as we all know, are the solid organs, like the heart, the liver, the lung. And at this point, we've been able to impact all 4 areas using regenerative medicine strategies.
So I have to ask just really, really quick, what do you think are the biggest barriers to producing a product that you can implant into a human?
Yeah, so, it takes so much work and effort. I think that's one of the things that is really not as obvious sometimes, is that it takes years really to get these technologies to patients. It really does. It takes, it takes over a decade really from the time that you even start to think about it to the time that you actually can put into the patient. Sometimes it takes even longer. It can take 2 decades. We've had examples of that as well. So it depends on the complexity of the tissue we're trying to create. But there are many factors, right? Cell harvesting, cell expansion, creating tissues creating three-dimensional structures. There are many, many steps along the way. So it's a very complex process, but like anything else, once you know the recipe, then it becomes easier to do.
Okay, that makes it sound super simple once you know the recipe is so I have to ask you, how did you get started in regenerative medicine and how did this what's the origin story of your lab in this area? And then off of that, right, as you've got started, how did you sort of go through the process of sort of figuring out the recipe?
Oh yeah, well, so I'll try to keep it brief, but basically, when I started doing this work, actually the term regenerative medicine had not been coined, had not yet been coined. So this is very early on. Uh, most human cell types could not be grown or expanded outside the body. Really, skin and just the discovery of growing skin cells had just occurred only a couple of years earlier. Uh, you know, Human cells could not be grown or expanded. Stem cells had not yet been discovered when we started this work. So it was really early on, but it was really, just a concept. Can we create tissue for patients? And so we really had to go through all those steps. How do you actually get cells to grow? And we were the first organ we targeted was the bladder. And and of course, just getting those cells to grow was a major challenge, right? Because every cell has its own origin, and it's really, we had to go back to how does the embryo develop? How does the human body actually develop these organs from an embryo all the way to a fetus, all the way to a baby? And of course, it had to do with a lot of the molecular genetics and growth factors and genes involved in getting these cells to grow. And once we figured out how to get the cells to grow, then it had to do, we need materials. So what materials are we going to use? Are we going to use natural materials, artificial materials? How do we get cells to grow on scaffolds? And then do they work in an in vivo model, and so on and so on and so on. So we really had to, you were really starting from scratch in many ways, because a lot of these things were kind of, just a concept really, but eventually it was something that we kept working at, and thankfully we were able to place an organ into a patient and made it happen.
So I have to ask what I'm sure is a very simple question, but what does it actually look like to 3D print a tissue, right? I can visualize a 3D printer, laying down layers of melted plastic, but how do you do that with stem cells?
Jeremy, that's also an interesting question because a lot of people think the printing is like this magic thing, you just push a button and out comes the organ. And nothing could be further from the truth. The printer really is really just scaling up your technology. You have to figure out all the cell biology ahead of time. You have to figure out the material sciences, how to mix these cells with these materials together so the cells can reconstitute and remain normal and viable and functional. And really the printer is basically just something that gives you that scalability and reproducibility. So you don't have to create it by hand every time.
So, Tony, tell us about some examples of successful implantations that your group has been able to move forward.
Yeah, so different strategies. So, for example, of course, the bladder was the first permanent replacement in a human that we did initially. And if we had known that back then, bladders were level 3 organs, right? So in terms of complexity, they were hollow non-tubular. So we had known back then what we know now, we would have never started with a level 3 organ. But by targeting a level 3 organ, it really made it easier for us to tackle level 1 and level 2 organs like skin or urethras, or blood vessels. And then we've been able to go all the way to solid organs, for example, for the kidney, using the patient's own cells, but using a strategy where you use a hydrogel and cells that you can put back into the kidney. So there many different tissues, cartilage, that we put into patients, muscle as well, skeletal muscle. So many different types of tissues depending on the indication.
Oh, that gives me a good follow-up. So there are a lot of different things that you hear, and maybe they're accurate and maybe they're not accurate. So I have some of those types of questions. So I kind of hear things about like ghost kidneys, which it sounds to me like a decellularization and a recellularization process. But then when we think of the 3D printing, that sounds more like something you're kind of starting from scratch. Is that true, or is one of those mechanisms more accurate for what has been done than the other?
It's interesting. When we started looking at solid organs, we really did not have the technologies necessary to create them. This is before 3D printing, before we had it all, we had scaffolds figured out. Remember, these were early days. People were still trying to figure out how to get normal human cells to grow. In fact, we had I used a slide in my initial talks several decades ago that showed the only human cells that could be grown, and there were only a couple. And of course, now most human cells can be grown and expanded outside the body. So a lot of advantages with progress in the field. But even now, 2020, even today, in this decade, you still cannot go to a patient, take a biopsy of their pancreas, and get those cells to grow and expand outside the body. Still can't, people still don't know how to grow those cells. So there's still challenges with cell biology. And certainly the same thing with scaffolds. We didn't have the technology necessary to create a solid scaffold. So really it was just an idea, and I remember clearly, I was walking, down the beach, and I saw this a piece of coral in the shape of a kidney. Then I saw this, and it had even a line along the edge of the coral, just like the kidney does, the Brodell's line that divides the kidney anterior and posteriorly. And then, of course, it was a coral, so it had all these pores in the coral. And I remember thinking, well, what if we could just use very mild detergents to wash the cells away of a solid organ, and then reuse the organ to reseed it and put it back into the patient? So that was really, kind of like an aha moment. Maybe can we get solid organs to be created? And of course, a lot of work has been going on in that area. And it is a strategy where you take an organ, a discard organ, because all these patients are dying every day. People are dying every day, and those organs are being discarded. So the question was, how can we actually take some of these discard organs and recycle them, if you will? You basically use very mild detergents to wash the cells away, and then repopulate them with the patient's own cells. Because the scaffold does not reject, as it doesn't have the cell once it rejects, but you can use the patient's own cells.
Yeah, I love the idea that, you're just going on vacation, walking around, and then you find some random piece of coral as an inspiration for how to, start to build or reuse these precious resources. I'm very curious to hear your thoughts on how, where we are today. And you mentioned some of the things that still need to be done, sort of basic research, cell biology wise, to understand and continue this. But you've also had great success, right? And so how do you go from bridging those two gaps, right? How do we continue the path forward and continue the success that you and your lab have had with regenerative medicine and organs, and start to grow them and enhance what we know to go forward? Like, what's the next generation of this look like?
Yeah, so there's still so much work that needs to be done, because every tissue is so different. Every tissue has its own properties. You have to go through the whole thing, the cell biology for that particular organ, the cells that it has. How do you grow them? How do you expand them? How do they retain their phenotype, their functionality? And, you have to start all over again with the biomaterials that you need to use. And you need to, each organ is entirely different. So there's still so much work that needs to be done because there's so many different tissues and organs in the body, and there's so much need. So the research needs to keep going forward. We've learned a lot from the past, so that's a good, a good foundation for the future. But we also used a lot of the foundations that we had from others in terms of cell biology and material sciences. So, you just got to keep building on that science and making sure that you keep moving forward to tackle more tissues and organs for patients.
So are most of these, or are all of these ideas autologous in nature? From an HLA perspective, we're always thinking about, how can we help? What role would HLA laboratories play in, an external organ being implanted in a person? So obviously, if it's all autologous, that's pretty great. And we're all looking to work ourselves out of a job. So I'm interested.
So absolutely. Well, as the interesting thing, of course, is that, the number of organs that need to be put in and the types of organs, there's still, I'm sure, decades and decades and decades more before you can eliminate the HLA issue, which of course is being worked on in so many different ways, right? So many different strategies. So I think we're still, a long time away. So I don't think the HLA world's going to be out of a job anytime soon, anyhow. That's for certain. But, we do favor the patient's own cells. It is a tougher approach, no doubt about it. I mean, I think that's one of the things that we faced early on, that people would say, well, it's just very hard to go and get the cells from the same patient. It's very much more complicated, and maybe it's better to get cells off the shelf, and that's better for industry because you just, can keep making cells from a cell line. But at the end of the day, the HLA issue is real. As nobody knows that better than you. The HLA issue is extremely real. And so for us, the strategy has always been use the patient's own cells if you can, because that way you can take a biopsy from that patient. You can grow and expand those cells outside the body. You're going to put them right back into the patient, and you don't have to worry about rejection. So that's been our absolutely preferred approach. It is tougher. It is harder. It's taken decades to get to where we are today. But I think for the patient, it's a nicer approach. And of course, if the patient does not have that particular organ, let's say that the patient, had only one kidney, and they get into a motor vehicle accident and they lose the only kidney they had. Now, what are you going to do? And I think that's where stem cells come in. And you can use, donor stem cells, that can give rise to all the 3 germ layers that don't form tumors. And then you can actually manipulate, some of the HLA features, but at the end of the day, you're still dealing with HLA issues under those circumstances. So certainly I always like to say we are an equal opportunity cell employer. We like the autologous cells, but if you can't get them, you got to use what you have.
Well, since you're not going to put us out of a job, at least I know now that I have good argument for taking walks along the beach to enhance my acumen in this area. I'm excited about using that to go to the beach and take a vacation. But you actually also kind of tap danced into an area that I wanted to ask you about. When we think about the future, and we think about the 109,000 people on our United States transplant wait list, for example, and we kind of think about just the vast nature of the need, we inevitably maybe have to think about scaling up. Do you think that some type of like universal stem cell or some other type of non-autologous stem cell source is eventually going to have to be utilized or commercialized as a potential kind of almost standardized way of producing certain tissues to meet the need? Do you see that as a future direction?
Absolutely. What a great question. This has been an area of high interest to us because in reality, there are many stem cell types out there, right? So you have the patient's own stem cells, but adult stem cells do not go into all three germ layers, right? They're mesenchymal. If you look at all the adult stem cells that you can get from a patient today, from bone marrow or fat or skin, they're all mesenchymal cells. And so the only way to get stem cells that go into all three germ layers is to use human embryonic stem cells or induced pluripotent stem cells. And unfortunately, the challenge with both is that they all form tumors. They'd have a natural tendency to form tumors. In fact, you cannot call a cell pluripotent unless it forms teratomas by the NIH definition. So you have these adult cells that, or even the perinatal cells with cord and cord blood, they're all mesenchymal, or you have the human embryonic or iPS cells. But there is one cell type that you can get at the time of birth that gives rise to all three germ layers, and that is placental stem cells. So there's a subpopulation in the placenta that can give rise to all three germ layers, ectoderm, mesoderm, and endoderm. And the only time you get that cell is at the time of birth. And the nice thing about that is that there are plenty of births every year. There are over 3.5 million births per year in the US alone. And a bank of about 100,000 specimens could supply over 80% of the US population with a perfect genetic match for transplantation. So I think that would be a great thing to do, to create a bank of cells that could create this HLA match. And now you have a universal donor pool of stem cells that you could use to create tissues and organs.
So new challenge for the community then, because I have a couple children and I don't even remember being approached to see if people wanted the umbilical cord cells. I certainly didn't have anybody ask me for the placenta. So we need to get the word out. We need some placenta. I want to ask a question in a totally different direction. With all of these, xenotransplantation, regenerative medicine, all of these amazing cutting edge, very scientifically complex options that are kind of on the horizon for patients. Some are, being done as you have done in some fashion already. We see a lot of the work around these studies coming out, not just in peer review publications, but in publications like the Washington Post and the New York Times. And when I see patients read these articles, I start getting I start seeing stuff on social media pages like, we can go off the wait list. The future of transplant is here. Did you see the thing about the artificial kidney? We're saved, right? And it kind of breaks my heart in a way, because these things are here, but not in a way that is necessarily being imparted by these articles. How should we be disseminating this type of information to patients in a way that is really transparent about where the technology is at and its availability?
I'm so glad you brought that up, because, I tell you what, the hype is just a terrible thing, because, these, people typically don't understand the timelines that it takes to get these technologies to everybody. And that's why, every time that we've actually published one of our tissue engineering trials, we waited at least until we had at least a 5-year follow-up in our patients before we ever published the work. That's been our pretty much our standard. And that is because, we just don't want to have one patient case, right? And the patient is now 3 months out. And now you're saying, well, this thing, look at this, and that's why, you have to be so careful. That's why anytime we publish one of these tissue engineered, technologies in patients, we We've done it in a series of patients, not just one patient. And we waited at least 5 years to basically say, okay, we know it works after 5 years. And then we still have a lot of work to do to make sure we can get it to more patients over time. But it's going to be, it's going to take years to get it through the approval process. And I think, and it doesn't happen just with that, studies that are published in mice. I mean, mouse studies that get published, and, as as well as I do, that there's a big difference between a mouse and a human, and pretty much you can cure everything in a mouse. So as the literature has shown. So I think we have to be so careful. And I think as scientists and as physicians and as journalists, we have to be careful, all of us as a community, how we interpret the data and to put it in the right perspective for the people who read about it.
No, I think you said that very well, and it's something that we've talked about on this podcast in a couple of different scenarios. And so, I want to thank you very much for that perspective and your time today. Thank you very much, sir.
Oh, thank you. I appreciate it. It's good being with you and Jeremy and Kelly. Thank you all so much, and looking forward to being in Montreal.
Yeah, that'll
See
be
you
awesome.
soon.
It'll be soon. Thank you.
Get ready for the must-attend event of the year in transplant science and immunogenetics. The ASHI 52nd Annual Meeting in Montreal, Canada, October 26th through 30th, 2026. Join world-class scientists, technologists, and innovators for cutting-edge workshops, interactive sessions, and breakthrough discoveries that are shaping the future of HLA and histocompatibility. Connect, learn, innovate. Whether you're a seasoned professional or emerging leader, this is the place to expand your expertise and spark new collaborations. Don't miss out! Be part of the conversation driving better outcomes for transplant patients everywhere. Register today and be inspired at the ASHI 52nd Annual Meeting.
Today we have a beautiful tea question, which comes from Cookie Larson from the Clinimmune Laboratory, who's curious about the future of transplantation, wanting to know, and I quote, "I want to help our newer techs prepare for the CHT and the CHS. What do you personally feel is the best way to study for these exams? Is it ASHI U? Is it reading the standards? Is it HLA Beyond Tiers? What is it?" Our lab is on the larger side, and we divide the sections of our lab into DNA serology testing and into the antibody testing. So some of the DNA techs have never seen antibody testing before, or cross-matching and vice versa, where some of her other techs have other things that they focus on. So this is an interesting situation. I've certainly worked in labs where the duties are split. There are technologists that work on nothing but molecular technologies and molecular diagnostics. And there are other technologists who work on all things antibody. I've seen that before. Jeremy, I bet you've seen it before. What are your thoughts on this question? It's a good one.
Yeah. I was actually in a very similar position when I was trying to study for the CHT, where I worked in a lab that only did bone marrow typing and didn't do any solid organ work. So I was in that a very similar position. Shout out, by the way, to the folks at IU Health who I was able to go over there, and they spent a week with me, just training me, teaching me about what they did for solid organ stuff. So that was critical. And so that's where I would start, is to say, if you are in a place where you are sort of specialized like that, that there's no substitute for spending time shadowing in those other areas, because the exam will expect that you're familiar with a range of testing methods and results and so forth. So I would say that's essential. I would say the ASHI U materials are very good and getting better all the time. and being updated all the time. So I think ASHI U is a great resource, and I think you hit on the standards as well, and the standards are a big part of it. And so I would say the standards should be in there. There is a study guide, of course, on the ASHI website that'll break down what is on the exam. And so that is a good guide as well. We talked about textbooks a little while back, and I don't think we got any responses. We had a textbook when I was coming up that was literally just called HLA. I've lost that textbook belonged to the lab I was working in, so I haven't been able to go back to it and sort of vet it anymore to see how good it stands up 10 years, 15 years down the road. But there are some textbooks out there that could be helpful, I'm sure as well.
I mean, I think something that comes to mind for me is if you've got a lab where you're not necessarily doing all of the areas that you would be expected to, and you're just doing DNA or you just do antibodies, right? I think this is an excellent opportunity for sort of the cross education, right? Where one staff member who does antibodies, for example, can give a short CE or short like presentation, right, of like what it is, why we're doing it to their colleagues, right? And sometimes I think that that's a little bit easier or better received than say like a supervisor or a manager or a director doing a CE there, which are all very good options as well. We've done those options in my lab there, and I think it's a good way of sort of, teaching each other different aspects. And I think I would like to call out the directors that are listening to this to take that on themselves and try and help that your newer members or the members that are showing the initiative that want to take this on and become certified to support them and to support them by giving presentations and helping them find resources, whether they're textbooks like Jeremy's talking about, online resources or publications to help them learn in that process. So I really want to emphasize that sort of leadership in for the directors and managers that are our audience as well.
Yeah, totally. The ASHI materials are great. They're so good. And you can build your own training library in your own lab. I know that every time I give a talk or a seminar or we're having a chat about a technology in the lab, we save all of those in a folder for lab-wide consumption. Of course, your SOPs, are there. Like pull out your SOPs, even if you're not the one doing them, and then generate questions and look at your transplant agreements. If you're more on the molecular side, and maybe you're looking more at hematopoietic stem cell transplant, and then some of your colleagues are looking more at antibodies applied to a solid organ and hematopoietic stem cell transplant, you can use those transplant agreements to kind of dig into, oh, well, we don't do that on this side. I wonder why they do that. And you can kind of chat with your colleagues and use those as a guide. So these are all suggestions for you. What a wonderful question and something that impacts people every single day. So Cookie Larson, thank you so much for that question. We greatly appreciate it. And don't forget, if you need career advice or have a question about something happening in your lab or department, visit our podcast page at ashi-hala.org/page/ASHI podcast, or email us at info@ashi-hala.org with the T, spelled TEA, in the subject line.
Today's Tech Talk is a special retirement shout out to Dean Silveria from Beth Israel Deaconess Medical Center. A colleague nominated Dean and shared this: "I've had the gift of working as his supervisee, and the lessons I've learned here are immeasurable. He's led our lab with kindness, compassion, and unwavering dedication. Dean has made an incredible impact on ASHI throughout his work developing ASHI University, serving as an ASHI inspector since 2000, and holding numerous leadership roles across the society. Dean, thank you for 4 years of service. I'm sorry, for your years of service, more than four, mentorship and commitment to our HLA community. Congratulations on your retirement, and we wish you all the best in this exciting next chapter. Thanks so much, Dean, and congratulations on your retirement.
Congratulations.
I'm still red. I'm still red.
Are.
He's amazing. I am still red. And not only are my cheeks hot, not only is he like what he's doing for science, for patients is just mind blowing. It's like the best type of science fiction that is real. It's not science fiction. Jeremy said it earlier. I can't take credit, but it's like, this is like the stuff that you see in movies. Like he is doing the stuff that you see in movies. And he's just a super, super nice person.
Would it be fair to say he's the LeBron James of regenerative organ medicine? That'd be fair?
I have not met LeBron James. Is he that nice? Is LeBron James that nice?
I don't know. I can't.
Yeah.
I've never meet. I'll have to meet LeBron James and compare and report back. So I'll work on that.
I think Tony's got him beat.
Probably, yeah. I mean, to me, one of the coolest things is that it's such a good story from conceptualization decades ago to the basic research that he and his lab have done for so long in the methodical and thoughtful nature that they have tackled the problem, right? To the like sort of fun, cool serendipity. I'm walking on the beach and I find this piece of coral and then I'm all like, let me just change the course of scaffolding, right? Like apparently we all need to go for more walks as we've talked about.
Yeah,
Like
that's
anywhere.
that's the point of today's episode is you
Take
need to go for more
home
walks on the
message.
Go
beach.
for walks on the beach. Yeah, I
Take
mean,
home message.
how many lessons are in that statement? Lessons about like stopping and taking in the moment and really, really thinking about your surroundings and what you can glean from them and learn from them, but also just really intense science, like identifying a problem and thinking back one level and realizing you have to go back further and further and further and further until you're literally at pluripotent stem cell science, and then building it back forward. It's just it's awe-inspiring.
And
Yeah,
it
and I think
also
go ahead,
it
Jeremy.
also cracked me up because who among us have not like seen a shell or seen a cloud or something and been like, that looks like a kidney.
Yeah, it is super relatable, super relatable. And I think it's the sort of natural, hardcore, basic research being not just done, right, but being done in a manner that enables the thought process of actual clinical implementation of that thing down the line, even if it's decades later, right? Like he talked about the intentional choice to use autologous and why he chose to do that, right? That these are decisions he probably made decades ago, right? And they've been working and building on. And I think that's important for our members in society to remember is that not only do these things take a really long time, but the basic cellular and molecular biology to go from A to all the way to Z is super impressive to get it all the way to the finish line.
And just the sheer respect for the patients, for where this product is going, for the science and the desire to really get it right and not rush it. Science is so competitive. But the purpose in this is really felt when you speak to Dr. Atala, and that is so it's just so inspiring.
Yeah, I think, don't forget that he has a featured topic presentation at our annual meeting. And if it's anything like what he did for our interview just moments ago, oh my God, that room should be packed to the gills to hear that man speak. So don't forget.
Absolutely. Yeah. If you're not doing anything else October 26th through October 30th, or even if you are, cancel that thing. Jeremy, cancel that thing and go to the annual meeting in Montreal in Quebec, Canada. You will hear Dr. Atala and others in the regenerative medicine speak. It's about the featured topic. It's the opener for the meeting. I can't think of anything more fascinating than being at that talk. So you should try to be there for sure.
All right. Well, before we wrap up, we've got another exciting coffee and compatibility giveaway. If you want a chance to win up to $150 in ASHI store credits, it is this easy to enter. So first, you just make sure that you subscribe to the ASHI HLA YouTube channel. And then when you see the promotional graphic for this episode in our member e-blast or on ASHI social media pages, you share it on your own social media account and tag ASHI. Then you just take a screenshot of your shared post and email it to info@ashi-hla.org. We'll randomly select one lucky winner to receive up to $150 in ASHI store credits, which can be used towards eligible ASHI offerings. That is pretty awesome.
That is pretty awesome. And listeners, please, please help us spread the word about the podcast. Introduce a colleague to Coffee and Compatibility, and you might just walk away with a prize. It's a win-win. So if you do that, if you listen to this podcast, thank you so much for your support. Be sure to subscribe, share, and tag us, and send us that screenshot. We truly, from the bottom of our hearts, whether ours or 3D printed, appreciate every one of you for helping us grow the Coffee and Compatibility community.
Until next time, guys. Bye.